Okay, today we are talking about the neuromuscular junction that happens there. So, um, what we have is the neuron, and we have the muscular junction. Now, we're just going to talk about how it is that the impulse that we got last time and that was propagating on the membrane of the neuron, how that it can be transmitted to the next excitable cell. And in this case, that is a muscle. So this is known as the presynaptic neuron, and this is the postsynaptic cell. Now, one thing that you should take note of is various activities happen in order for this communication to occur. And this communication can be of two types, or noted as two types. We have electrical transmission, that is noted in cell to neuron communication. And we also have the chemical transmission. This chemical transmission involves what we call neurotransmitters. So these are chemicals that are used to transmit the impulse from the presynaptic cell to the postsynaptic cell. And an example of this is the neuromuscular junction, which we're looking at today. And at the neuromuscular junction, we have a neurotransmitter known as acetylcholine. Now, acetylcholine, we have choline coming in from the GIT, and also we have some choline that comes in from the synapse itself. It's transported back into the neuron. Now, vesicles that are coming from the cell body, clear small vesicles, they come empty, and then we also have mitochondria, okay, which produces acetyl-CoA. Now, acetyl-CoA plus the choline will give us our SCH. Now, this acetyl and the choline is what gives us our final SCH, as I have said, and the SCH is stored in the vesicles that are coming from the cell body. Okay, so it is then stored in the vesicles that are coming from the cell body. Now, there are two things that I should just remind you of here. Number one, that this combination of acetyl and choline is made possible by an enzyme, and this enzyme is known as the choline acetyltransferase. Okay, now once you have our SCH and it is in our vesicle, we need this impulse in order to release it. So the impulse that is coming, or the action potential, or the wave of depolarization and repolarization, is going to activate the calcium voltage-gated channels. Now, these voltage-gated channels will allow an influx of calcium. An influx of calcium is going to work on two types of proteins that are noted. One is noted on the vesicle itself, and another is noted on the membrane of the neuron. Now, these two have names, and we have synaptobravin that is noted on the SCH vesicle, and we have the syntaxin that is noted here. Now, once these two bind, you will note that this component where the binding takes place dissolves, and what you're going to have is exocytosis of the components of the vesicle. Okay, so once the SCH reaches the vesicle, we have SCH receptors on the membrane. Now, this is the end plate, the motor end plate, we have receptors that are known as nicotinic, and they are known as nicotinic simply because nicotine can also bind to these receptors. So the nicotinic cholinergic receptors. So these nicotinic cholinergic receptors uh, can allow SCH to bind, and once SCH binds, they undergo a conformational change, which is a change in structure, and this will allow ions to pass through. Now, take note that at rest, which the cell is, we have already what we discussed in our first video, that the permeability to potassium is there, but at rest we find that the potential here is closest to the equilibrium potential of potassium. Therefore, potassium um, will be at equilibrium, so to speak. So what will be allowed to pass more is the sodium, and as the sodium comes in, we find that it creates a local depolarization. Now, this local depolarization is noted as a local end plate potential. Now, as sodium keeps on coming in, you'll find that it will reach threshold. So, again, we go back. Once it reaches threshold, it's going to open adjacent sodium voltage gated channels. Okay, and once it opens those, there's going to be an influx of sodium, and that is what's going to cause the action potential depolarization. And we go back to our story before it could reach the equilibrium potential of sodium. We're going to have the inactivation gates closed, and at the same time, we're going to have potassium voltage gated channels open. We're going to have a repolarization, and it's going to hyperpolarize because it will try to get to the equilibrium potential of potassium, but we'll see it reverting to the resting membrane potential, rather, like that. So after that, we go back to our story where there is propagation, and after propagation, we find that this is what causes contraction in muscle, which we'll talk about in the next video. So for now, that is all we have.